Did you know there's a weird current that flows through all of our power grids but delivers no power to our homes or factories and is a real problem for the power companies? Well, there is, and that's what this video is all about. And to get started, what we should do is look at some devices and see if we can find some examples of that weird current. Well, let's see if we can find this weird power that I'm talking about. And to do that, we'll start off with a little cheap power meter. And it's plugged into a power bar. And off screen, this power bar is connected to a GFCI device for safety. And what we'll do is we'll use a little quick test gizmo to connect the power meter through a ammeter, which we'll turn on, to a transformer. And this is one of the transformers we used in a previous video, if you happen to see it. And, well, we'll hook this to the live connection. We'll hook this to the neutral connection and hook it to the transformer. And maybe what I'll do is move the transformer a bit out of the way because I don't want to get close to that live contact. And, well, let's turn on our power. Do we have power? We do. And here's our little power meter device showing we have 121 volts AC. And I'm going to close the quick test, which should connect the transformer. And it did. And we can see the transformer is drawing somewhere around 30 milliamps or so, according to the ammeter over here. And at 120 volts or so, that should be somewhere around 3.6, 3.7, close to 4 watts of power that's being drawn by the transformer, even though it's connected to nothing. All right, well, let's press this button and take a look. And yep, we're seeing about the same current on the power meter as we are on the ammeter. I would suspect this thing is a little bit less accurate, but either way, they're close enough to confirm each other. Well, that's very nice. We'll press the button one more time and see the power. And here's the strange thing. We're only consuming 1.4 watts, so somewhere around, I don't know, a third or so of what we were expecting with that current. And, well, that current has not changed. So something weird is going on. And, well, that's probably the first hint that there is something strange going on with current, and not all the current is actually carrying power. Well, this is a really cheap, simple transformer. What we should do is look at a more common inductive type device. And I should point out this is an inductor, as it's hooked up right now, as is any transformer that's not connected to a load. We'll look at a very small induction motor, the most common motor in existence, and see how it behaves. All right, to see what an inductive load looks like, we're going to use this little bench grinder that is at least somewhat inductive. And we'll power it with this power bar, which I'm going to conveniently put through the handle of this saw. And we have our little power meter that we'll plug in right here. And we will plug our bench grinder into the power meter. So what we should do is turn on the grinder. And immediately we see the voltage drop. And now it goes up again. That was because it drew a lot of startup power. So let's see what we get. Current is 1.35 amps. Power is 98 watts. That's sort of strange. You would expect the power to be a bit higher if we multiplied voltage and current together. So the induction motor behaved much the same as this little transformer. Let's look at a 10 microfarad capacitor a typical running capacitor for a small motor and see how it behaves. I've hooked it up the same way. The power's coming in through the power bar, through the power meter, going through the quick test and the ammeter so we can see the current, and now it's attached to our capacitor. And we'll turn things on, and with a bit of luck, well, I'm just going to press this so we can get to the, oh, I hit the wrong one. There we go. So again, 121, 122 volts or so. We've got about 0.43 amps flowing according to the ammeter. If we switch the power meter to its amp function, it says 0.46. Again, close enough that they're in reasonable agreement. And we'll press it one more time and look at the power, and the power is a 0. So this is a great example of almost half an amp flowing that would normally give us about 50 watts, and yet we're seeing no power flow at all. Well, you might be saying, okay, it's clearly this power meter that's all messed up. So what we'll try is we'll try replacing the capacitor with a 100-watt electric light bulb, and if we're lucky it won't simply wash out the video. Here we go. Well, we can still see the meters. Well, the power is showing 91 watts, so it's clearly not the greatest or most accurate electric light bulb, but it's good enough. If I get the right button. There we go. We're at about 120 volts or so. So that's what we would expect. We have a current of about 0.75 amps. Again, that's almost exactly what we would expect to get 90 watts. And there again is the 90 watts of power that this lamp is actually consuming. So clearly the power meter knows what it's doing, at least for a good old resistive source. So what is going on with things like capacitors and transformers or motors? I think the best way to see is to use an oscilloscope, and I'm going to hook that up now so you can see exactly what's happening. So to investigate things further, what I've done is brought in my old oscilloscope, and because it's so long we can't have it facing up at the camera. So what I'm going to do is turn it on, and we will use a cell phone to video it. There we go. And in place of our power meter, what I'm going to use is this box, which will allow us to visualize both the voltage and the current from this power outlet on the screen of our oscilloscope. And maybe what we'll do is, well, we'll get rid of our trusty little quick test, and we'll hook our current box into the power bar. Actually, why don't we use the power meter? Since we've got it anyway, it won't do any harm, and it may help. There we go. All right. We have some of the devices we're going to test. And what I need to do is hook the test box to the oscilloscope. So we'll attach the neutral of the test box to ground on the scope, and to try and keep color conventions, we'll use yellow for current, and I'm going to hook it into the input of the second trace, and the closest thing that I have to purple is blue for AC voltage, and we're going to hook that into the first trace on the scope. And I'm just going to adjust my little cell phone camera. That's probably okay, I think. We should start by turning on the power, and there we go. This trace over here, the upper one, is showing us the AC sine wave the 120 volt RMS sine wave that's coming in from the power grid. And if I take this light bulb and we'll plug it in here, there's the current. Maybe we'll move this thing a bit out of the way of the bulb so we can read it. And once again, we can see we're producing, well, right now it's maybe 94 watts or something like that. Maybe the voltage is a bit higher. Doesn't seem to be. Who knows? Again, close enough for our purposes. The most important thing, though, is the current is on this lower trace over here. And if we match up the current and the voltage, we can see that they track just almost perfectly. And I think we're ready to plug in the quick test and see what the capacitor does. Oh, and there we are. Look at that. Well, we see a couple of weird things right now. And I'm just going to move the current through the capacitor. Well, the first thing we see is a whole bunch of weird bumps and noise on what should be a nice, perfect sine wave. And what it is if you've had calculus, the capacitor is essentially doing a differentiation. And what that means is it emphasizes every change in voltage. So where we get sharp edges, like if you see here, the sine wave up top is somewhat flattened, and then it goes straight down. Well, that's a very sudden drop, and that corresponds to a sudden drop in the current through the capacitor, or a sudden increase in the negative direction. What you have to sort of imagine is that this nasty, messed up sine wave through the capacitor is indeed a very nice sine wave, just like the sine wave going in. And if you look at it, what you can see is the lower peak of the sine wave is preceding the lower peak of the voltage, and the upper peak of the current through the capacitor is also preceding the upper peak of the voltage. And in fact, what you can see is that upper peak corresponds to the halfway point or 0 point of the current, of the voltage going into the capacitor. So what we can say is that is preceding, the current is preceding the voltage by 1/4 of a AC cycle, or 90 degrees. And that is exactly what you would expect from a capacitor. All right, here is our nice little transformer. Once again, we will hook it up. It doesn't help that I can't see behind the black box. I don't have X-ray vision. There we go. There's our transformer hooked to the quick test, and I think we're ready to plug things in. Now, there should be a lot lower voltage on the current because we know that transformer only pulls about 30 milliamps. And can I do it here? Okay. Well, you can see how little current. Oh, there we go. That's better. What we have is our nice smooth input AC voltage and a somewhat distorted and spiky current going through our nice little inductor, our transformer. And without going into details in this video, what we're seeing is most likely saturation in the transformer core at various parts of the cycle, causing these sort of flattened areas here and peak currents over here. But again, if we sort of look at these peaks and these peaks down here as if they were the peaks in the normal or idealized sine wave that we should be getting in a perfect world, well, once again, we can see they're occurring at the 0 point of the voltage. So what that means is the peak of the current is delayed from the peak of the voltage by a quarter of a cycle. In other words, by 90 degrees. So we, in fact, have exactly the opposite thing happening for an inductor as we did with a capacitor. The capacitor caused the current to precede the voltage by 90 degrees. The inductor causes the current to lag the voltage by 90 degrees, and this is a very typical behavior. Well, what we should do is maybe draw on a piece of paper a more ideal situation where the current through the inductor is sinusoidal the way it should be, and for that matter, the voltage going in is sinusoidal the way it should be. You'll notice it's kind of flattened on the top of the sinusoids here, and that's because of all the electronic loads we have these days that tend to skim the power off the tops of the cycles and must be creating havoc in the power grid system these days. So let's look at the power flow now that we've seen how these two types of devices either delay or cause the peak of the current to precede the voltage going into the capacitor or inductor. So just to remind ourselves what we're dealing with, what we have is an AC source, which we draw like this, and that, of course, is the grid, and we actually give it a plus and minus sign because in many situations what we have to do is keep track of the positive and negative parts of the cycle. And indeed, what we would do is, because we decide arbitrarily that the source is at 0 degrees, it's our reference point, we will label the voltage like this, 120 volts at an angle of 0 degrees. Then what we do is we have some sort of a device here where we can measure that voltage, and that was either our nice little power meter gizmo or our much bigger gizmo we use to feed the voltage and current values to the scope. So maybe what we'll do is just draw a box here and we'll say measure to remind us that it's going through some sort of a measurement box. And then, depending on what we're looking at, it might be, in this case, an inductor that we're examining. And to be realistic, because we certainly know that this little transformer here was using something like 1.5 watts, well, we can also say there is a resistor in parallel with the inductor. And this is our loss. Whatever's causing the losses, be it the core, be it the copper and the windings, whatever, we'll represent that as a resistor, and I've just drawn it dotted to differentiate it from the coil, which is indeed a representation of what's exactly in the transformer. Okay, now what we did find, and this is going to be an example of how good or bad I am at drawing things. This is essentially going to be what we saw on the oscilloscope, and I'm going to mark off points here that represent 90-degree points on a cycle. And I'll see if I have another pen that works. See if the blue works. What we'll do is we will draw in our 120 volts at 0 degrees, and by convention we start off with assuming it's a cosine wave. So the cosine starts off at some value over here, and then during 90 degrees it comes down like that, and then somewhere over here at the 180 degree point the cosine comes down like that, and now it repeats itself and does this, and then up here it goes up and over and comes down like that, and well, once again goes down over there. So this is our voltage. So we're now going to draw our current in purple, and the current going through our inductor is lagging. So I'm going to draw some dots here to try and make it a bit easier to draw. So here's our current. It comes to a peak at the 90 degree point, and then at the 180 point it goes down to 0, and then down here 90 degrees later it comes up again to a peak, and then over here it goes down to 0, and then up here it comes to a peak again, and then it goes down to 0. So this is I, the current. What we should do is maybe make it very clear that I is going in this direction, and we should also make it very clear that this is the voltage we're talking about over here. We did say that this current here is delayed, and what we really need to do is use the good old power equation. Power equals voltage times current to try and figure out what the power is during this cycle. Well, 0 times something positive is 0. Some mid-sized positive value times some mid-sized positive value is something in the middle. And then 0 times a positive value is 0. And we can now carry that down over here. 0 times something big is 0, and something mid-sized positive times something mid-sized negative is negative. So what we get, it turns out, is a funny little sine wave in here. And we can repeat the process. Over here we have some mid-sized negative value times some mid-sized negative value. Surprise, surprise, negative times negative is positive. So that comes up to here, and then over here 0 times a positive is 0. Over here, what do we get? We get a negative, and it sort of does this. So this is our power. And you might be going, well, isn't that weird? The power is positive for a small chunk of the cycle, and then it's negative for a chunk of the cycle, and then positive and negative. The power is rapidly switching from positive to negative to positive to negative. Well, what does positive power mean? Positive power means that we have power coming from our source to our load. So over here, during this tiny section of the cycle, this quarter of the cycle, we have power going into our inductor. During the next small section of the cycle, we have power going into the other direction. And indeed, if we look at this, these two parts of the sine wave are identical, but just opposite in sign. So all the power that we shoved into the inductor over here is now coming back. And it just repeats and repeats and repeats. So we have power going into the inductor and then going right back out and then in and then out forever. What does that mean? Well, we do have a current flowing. We've measured it. We've seen it both on the ammeter and the power meter. We do have voltage, and normally we would say the current times the voltage is the power, but in this weird situation, we have power flowing, but it's actually just going back and forth, so there's no net power delivery in either direction. And what this is called is reactive power. And the normal power that we have, where it's all going in one direction, is called real power. And if we take this current times this voltage, and don't worry about whether they're offset in phase or not, we get what is known as the apparent power. So that's what that weird current is. It's current that's going in and out of something like an inductor. Now you might be saying, what about this capacitor? What's happening there? Well, if you were to redraw this with the current now shifted over in this direction so it precedes the voltage, what you'd find is you would get exactly the same sort of power going in, power coming back, power going in, power coming back. And maybe what we should do is draw this same thing for real power like we saw in the light bulb. Well, we'll maybe do that real quickly. Hopefully I won't mess up. We'll once again draw our voltage, which comes down here and then peaks over here and then comes up here and then peaks over here and continues on. That's our voltage. But if you recall, for our lamp, for a resistive load, the current was in phase with the power. I'm not going to draw them quite at the same level, but I will draw the current just a little bit less, just so we can see them and the felt pen marks are not on top of each other. Well, what happens when we do our power equals volts times current? Well, maybe we'll just remind ourselves again. Purple is current, blue or maybe green on the video from the yellow is voltage. Well, what do we have here? We have some positive times some positive. There we go. We have 0 times 0 is 0. We have a negative times negative. What do we get? We get a positive. We have a 0. Positive times positive is positive. 0 times 0 is 0. Well, you're probably beginning to see the picture. What do we get? We get power that looks like this. It's another funny little sine wave, just like we had up here, except that it is all elevated above the 0 point. So what that means is we have power flow going from the source to the load here, and then it sort of gets less and less and goes to 0, but then instead of going negative, it goes back up again. And so what we're getting is bursts of power being transferred into the resistive load. And that's indeed what we would expect, right? We have an AC voltage that's going up and going to 0 and then going down and so forth. Well, it's clearly sending voltage and current in pulses. We would expect the power to be pulsing, and indeed it is. So that's the difference between reactive power, where that funny little power waveform is such that the power goes back and forth, and real power, where even though the power pulses, it's ultimately all going in the same direction. And what happens if you have some combination of these two? Well, everything adds together, meaning these power waveforms add together, the currents add together, and we get a combination of power that has reactive parts and real parts. And it's the real part that transmits the real power from the generator to our load. It is the reactive power that just goes back and forth, but even though it's not transmitting power, it's still a real current that's flowing on the AC line. And this is a real problem, because if you have something like a relatively large induction motor that's maybe using 1,000 amps of real power, because it's consuming a lot of power driving some big piece of equipment in a factory, well, it might have 500 amps of reactive power, and we could add the two currents together, and they don't add as you might add normal currents. They actually add as a vector sum. Future video. So you get something less than the sum, but it's still considerably more current than if you had no reactive power at all. So it is a problem. And even worse, when you have something like a transformer idling, it will still continue to consume the reactive power, as we saw on this little transformer, except without delivering any power to a load. Well, that's a complete waste, and worse, it's forcing the power company to supply all that reactive current to the transformer. And that current, because that current, even though it's out of phase, is flowing through the resistance in this power line, it is indeed heating up that power line due to I squared R losses, because the power line actually has some resistance in it, because we don't normally use superconductors because they're too expensive. So that reactive power is a real problem, and what power companies do is, for consumers with gigantic reactive loads, and that's typically factories, well, they require them to do something about that reactive power to try and get rid of it. And one of the ways you can get rid of it, certainly for smaller reactive loads, is to use a capacitor, because most of those reactive loads are things like induction motors. So like a transformer, they have a lagging current. Well, if we supply a leading current with a capacitor, that cancels the lagging current and gets rid of the reactive power, or a good part of it. And, well, we should do that with our little bench grinder and see if we can use this capacitor to get rid of most, if not all, of the reactive current, the reactive power, and just leave the real power. All right. So what we need to do is connect this plug from our quick test, which connects the capacitor, to the same circuit as where our little grinder is attached. And we will do that by using a triple plug like that. And I'll just plug it in here. There we go. And if we change the current dial on the power meter shows 0.46 amps. The ammeter shows 0.45 amps. That's pretty close. Just for fun, let's look at the power. And the power is 0, which is showing how good a capacitor that actually is. So we'll go back to amps, and let's turn on our device and see what happens. Well, here we go. We're drawing 0.4 amps on the ammeter. In other words, that's what this capacitor is drawing. But our total current, as we see in the power meter, is 1 amp. So we've gotten rid of 0.45 amps of reactive power. And let's look at the real power. There we go, 96 watts. That's exactly what we had before we attached the capacitor. And maybe just to show you how true that is, I'm going to disconnect the capacitor. The total power has not changed, or not changed significantly, but if we go back to amps, you can see we have about 1.3 amps, so about 0.3 amps more than we did with the capacitor connected. And we'll connect it again. There we go. The current goes down. Isn't that cool? Now, imagine if we had a motor 1,000,000 times the size, or even 1,000 times the size, drawing 1,000 amps. We'd be saving 300 or 400 amps just by doing this, and the electric company would be really happy. Well, that's the weird current that flows in our power lines, and for that matter, it's accompanied by that weird power, that reactive power that does not provide any useful power to our loads, but does create an annoying current that the power companies have to handle in larger transformers and generators, and for that matter, that does result in power transmission losses because of the current flowing through the power lines that have small amounts of resistance in them. The interesting thing is, if you look at all of this mathematically, it turns out that complex numbers represent all of the AC voltages and currents and phases quite nicely. In fact, so nicely that we use them all the time in electrical engineering. And when you crank through the usual equations for power and come up with a value, you get a complex number. And the real part of that number is the real power, and the imaginary part of that number is the reactive power. So in a sense, reactive power is imaginary power. It's not power that's being delivered to the load. So there is a very nice mathematical representation of everything we've talked about. This whole video was inspired by a number of discussions and questions from a previous video, and I'm starting to do more and more videos based on viewer questions. So if you have a question based on this, or a suggestion for the topic of a future video, please put them down in the comments below or send me an email. And if you do either, let me know what your name is and where you're from, because it's always nice to give a bit of credit to who suggested the topic. And, well, see you next time. I certainly hope you enjoyed this video.